Welcome back, students, to our Chemistry 1510 video notes. In this video, we're going to talk about electron shells, subshells, and orbitals. So the Schrodinger wave equation, which, mind you, I accidentally spelled Schrodinger wrong, there should definitely be a D in that, is really just a big math function. And like any other math function, it has a solution, and that solution, when graphed, is a 3D map of where an electron spends most of its time. And this 3D map is called an orbital. Within the atom, there are layers of electrons and locations where those electrons can live. This is kind of like the layers of your address for your house. So let's talk first about the definition of an orbital. The orbital is just a region of space around the nucleus where you can find an electron the majority of the time, about 90%. So this is where an electron lives in the most specific area, and an orbital can only contain a total of 2 electrons. So a subshell is different than an orbital. A subshell is a kind of like an orbital type. These types of orbitals have letter designations of S, P, D, and F. So our subshell is really a group of orbitals that all have the same energy. When orbitals have the same energy, it's called degenerate. So the types of subshells are called S, P, D, and F. And as we'll see later on, each subshell contains a specific number of orbitals.
S, P, D, and F.
Yep, that was S, P, D, and F. So, a shell can also be referred to as an energy level. So that would be N that we've seen before. So this would be the energy level where the electrons are. Sometimes this is also referred to as the principal quantum number, which we'll get to later when we talk specifically about quantum numbers. So let's look at some shapes of orbitals. Here is your s orbital. Your s orbital is a sphere.
Mama, are you using this computer right now?
1 second. All right, so the s orbital is spherical. The p orbital, it has this kind of lobe dumbbell shape type thing. The d orbital has essentially kind of like a 4-leaf clover type thing going on. It almost looks like 2 p orbitals put together, except for this last one, which looks like a p orbital with a ring around the middle. So all of these orbitals are going to be what's called degenerate with respect to one another, meaning they have the same energy. Notice how your s orbital, there's only one of these. So there's inside an energy level, so inside a shell, there can only be one s orbital. Wait, I don't want to say that because you might get confused. well, I think I'm going to have to say it anyway. So inside one shell, so if we're talking about shell number 1, you can only have a singular s orbital. If we talk about shell number 2, you can then have the option of p orbitals, and there's going to be 3 p orbitals. There's going to be 5 d orbitals, and then we don't have f orbitals pictured, but there's going to be 7 of those. So when we talked earlier about how your subshell has certain letter designations and how each of those subshells contain a certain number of orbitals, your S subshell has 1 orbital, your P subshell has 3 orbitals, your D subshell has 5, your F subshell has 7. So let's look at an energy level diagram to try and make this simpler in a pictorial fashion. So here we are, we have all of our s orbitals, all of our p orbitals, all of our d orbitals, and all of our f orbitals. They are arranged with respect to energy, where the lowest energy orbitals is down here and the highest energy orbital is up here. So your 1s is your lowest energy orbital. Then next comes your 2s. Then comes your 2p, then your 3s, then your 3p. Notice how you might think 3d comes next. But once you get to this point, the orbitals' energies are very similar to one another. And so the 4s actually comes before the 3d. Now you might think that's an obnoxious thing to memorize, but I'm going to show you a way around simply memorizing those weird exceptions. But first, let's talk about filling these energy level diagrams. So each of these little blanks, right? So each of these little sections, these little lines, stands for an orbital. And one orbital can only have 2 electrons in it. So if we look at something like oxygen that has 8 electrons, what we're going to do is we're going to put electrons in the lowest energy orbital first. So I'm putting 1 electron in my 1s, and then I'm putting a second electron in my 1s.
You are done with work.
I'm not all done with work. I have to finish this video.
Apples.
Oh, good. Okay, so we have our 8 electrons for oxygen. We're putting our electrons in the lowest energy orbital first. Notice how 1 electron is pointing up and 1 electron is pointing down. When you see this, this is a Pauli exclusion principle, meaning that the electrons have to have opposite spins because they can't have the same quantum numbers when they're in the same orbital. You don't know what quantum numbers are yet, so you're just going to pair the spins, 1 up, 1 down. So then you come into the 2s, 1 up, 1 down. So we've used 4 electrons. Now let's put in 1, 2, 3, and then come back and pair with number 4. So we just employed Hund's rule. Hund's rule is electrons in the same subshell have to remain unpaired when possible. So that means I spread out my electrons in the 2p before I came back and paired them. So now let's do potassium that has 19 electrons. We start at our lowest energy level, we fill those. We come into the 2p, we spread them out, but we haven't reached 19 electrons yet, so we have to come back in and pair them. We've got 2, 4, 6, 8, 10 so far, 11 and 12, 13, 14, 15, 16, 17, 18, and 1 in the 4s makes 19. So this is how you would fill an electron energy diagram. You would use these 3 principles here. In another video, we'll talk about shortening this diagram in electron configurations. Thank you so much for your attention and your patience with my children. This is Katoni signing out.